So I'm Shoini Deshi. Today I'm going to give a presentation on the simulation of wireless reality manufacturing process using PravaH and also represent the multiple evolution of the same using one of our validated case studies. So first we are going to take a quick revision on the directed energy deposition process, that is the DED process. So DED process, as we know, it is a 3D printing process that uses a focused energy source to melt and deposit material onto a substrate, building parts layer by layer. And based on heat source, DED process can be classified into three types, that is electron beam DED, laser DED, and wire arc DED. Here goes the picture representation of the electron beam DED and wire arc DED, and then we have the laser DED. So among all these process, laser DED is the most preferred ones because of its better control over heat input. It uses wire or powder as the feedstock material. It also has small heat affected zone, and it has high material deposition efficiency. So the WLAM process in PravaH software also follows laser DED process. The module in PravaH software enables the user to perform detailed simulations of wire laser directed energy deposition process with the focus of analyzing the melt pool dynamics. So it mainly solves equations for fluid dynamics and heat transport, and it uses the FVM scheme. It's a finite volume method scheme to solve the discretized differential equations, and it also captures the complete physics involved, that is the phase change, laser dynamics, heat and mass transfer, temperature dependent surface tension, Marangoni convection, and gas entropy. Now you can get a closer look on the wire feed laser DED process, where you can see that the laser beam melts a metallic wire, creating a molten pool that solidifies into a layer of desired path. The next thing we're going to explore what is Marangoni convection. So Marangoni convection is, as we know, it's the fluid flow inside the molten melt pool due to the surface tension gradients. Now, this in this diagram, this diagram will clearly portray the movement of the molten melt particles due to the surface tension gradient. So mainly what happens is that the transport of laser energy from near the laser axis to the outside of the melt pool through fluid transfer, but not through heat convection currents. To explore the basic physics, we can say that the difference in temperature in the melt pool actually leads to the difference in surface tension. And this difference in surface tension creates a force that drives the fluid flow, which introduces convection currents within the melt pool, and it affects heat transfer and material mixing. So this whole process is called the Marangoni convection. And all this physics is captured in PravaH module, WLAM module of PravaH software. So next, I'm going to introduce you to the GUI interface for macro scale WLAM. Here, as you can see, that under the settings section, there are three icons: material, process, and simulation. So this material section actually allows users to select the material and define its thermophysical properties for all three metal phases and the surrounding inert gas. Users can also create a new alloy of their choice and specify its properties. So for the material properties, you need to choose an alloy from the drop-down list. There are some alloys, and the respective properties are already loaded in the software. The mostly used one is the Ti 64 alloy, as you can see in this picture. So one thing to keep in mind in this material properties section is that the chosen material properties are applied for both the substrate and the feed wire. Now, three kinds of alloy properties are available. That is the solid alloy, molten alloy, and vapor. You can see here the solid alloy properties that are available. They include molecular weight, density, thermal conductivity, latent heat of fusion, specific heat, absorption coefficient, emissivity, and Lie constants. So these are the properties. In case you want to create a new alloy, you can specify it according to your own choice. Now here, under solid alloy properties, there are three temperature dependent properties, that is the density, specific heat, and thermal conductivity, for which you have to give different values at different temperatures in a tabular form. So yeah, this goes for material properties. And similar way, we can give the molten alloy properties, as you can see, and the vapor alloy properties. And we also have an option to enable or disable vaporization in the simulation. So this thing, by disabling vaporization, actually reduces the computation time, and it's recommended for processes where the vaporization has minimal effect on outcomes. So there is this operation also. And now we'll go to the shielding gas. So what is shielding gas? In WLAM, shielding gases plays a crucial role in protecting the molten metal and the heated area from atmospheric contamination, ensuring the quality and the integrity of the final product. So as default, we have loaded three shielding gases and their respective properties, that is the for argon, nitrogen, and air. User can also create a new shielding gas describing the different properties. And here goes the schematic view of the shielding gas in WLAM process. And then you can see what are the shielding gas properties which you can specify in case you need to create a new shielding gas. That is molecular weight is there, specific heat, dynamic viscosity, Prandtl number, and density. Now moving on, we are coming to the WLAM process. So clicking on the process icon under the settings section will take us to this GUI interface where the users can input their desired process parameters in the form of leisure properties, wire parameters, and initial chamber conditions. Yeah. So under leisure properties, we have laser beam component, power, D4 sigma meter or spot dia, and Fresnel coefficient. So for the leisure properties, the first comes a leisure beam component, where we have this -1 along the Z direction as default. This means it's a simple thing. It's a default leisure orientation. This means the leisure is directed downwards. And then we can also specify the leisure power, as you can see. And the next point comes the spot dia. So the spot dia is the measure of the laser diameter. It actually characterizes how the laser energy is distributed inside the spot. And then the last is the Fresnel coefficient. It actually influences the laser absorption and reflection to the substrate and the melt pool. Moving on, we are going to see the Y parameters. Under Y parameters, we have Y radius, Y substrate clearance, interlayer clearance, feed rate, and feeding angle. From this pictorial representation, you can easily see what you mean by wire substrate clearance. This is the distance between the tip of the wire and the substrate. And in this picture, you can understand what we mean by interlayer clearance. So then we have the initial chamber conditions under the process parameters. Initial chamber conditions, we have preheat temperature, initial substrate height, chamber pressure, substrate clearance at boundary, and the units are also given, as you can see. So this is what we mean by substrate clearance at boundary. This is the clearance that we give before this initial point from where we are starting the process. And then we have this initial substrate height. So now that we have covered the process parameters, we are going to move on to the scan pattern. So for scan pattern, there is an icon there in the GUI interface, upload scanning pattern. On clicking on the upload scanning pattern, this will navigate to your project directory. The system will automatically create a WLAM folder within your project directory. Inside the WLAM folder, default scan patterns are provided in the data folder. You have to select the desired .csv file. You can see here that within your project directory already, there are three scan patterns which are loaded in the software as default. They're already there, and you can select one of them and click open to upload the scan pattern. The pattern will be uploaded and applied to the simulation automatically. Now you can also create a new scan pattern for yourself to like regulate the leisure according to your own choice. So here I will show you how to create a scan pattern of your own choice. So for reference, we are taking the pattern default.csv file, where we are considering the single layer, single track movement of the laser. The laser is on from 0 to 0.375 seconds. During this time, the laser scan over a track of length 8 millimeter with a scan speed of 0.0213 meter per second. So now you must be thinking that, oh, what are these values and how we are actually coming to these values. To start with is that we are actually considering a track length. Let's say 8 millimeter we are considering here, and we are also considering the scan speed, which is 0.0213 meter per second. From this values, we are calculating the deposition time. That is the deposition track length by laser scan speed. That is the speed equal to distance by time, simple formula. You can calculate the deposition time from here. And then with these values, we are going to create our scan pattern. So the scan pattern has these columns. The first goes for layer number, which shows us the layer number we're operating on. Then comes the simulation time, laser position in x-axis and y-axis. Then comes the laser height, and then comes the laser condition, which can be specified as on or off. Now for the single layer track, first layer goes for layer 1, when we are specifying the initial time as 0 and the laser position as 0 and 0, both x and y-axis, because we are starting from the origin. And here the laser height is 0.0075 meter. And now at this condition, the laser condition is off. That is, laser has not yet been started operating. The next row will show you that this is a single layer track, like single layer track deposition. So the layer number will be the same, that is 1, and the simulation time is 0.375, and the laser has reached 0.008 meter, that is 8 millimeter, and the laser height remains the same, and then the laser condition is on here. And for the last row, we are having the layer number as 1, as obviously it will be constant until the from 0.375 seconds to the 1 second is the cooling time, because after 0.375 seconds the laser is turned off, and this we give for the cooling time, and we are then turning it off at 1 second. So this is how you can create your own scan pattern. And then we are going to see the default scan patterns that we have already loaded in the software. That is a Z-shaped deposition pattern. You can see this is the visualization of the Z-shaped pattern, and this is the table for that. And as I've already told you, these are the this is the deposition time values, which are calculated from the same formula using whatever value you're considering as scan speed and track length. Now there is another default scan pattern, that is 4-layer 4-track square shaped deposition pattern. You can see this is the visualization, and this is the corresponding scan pattern table for that. Now next we will see about WLAM simulation. So the third icon that we have is the simulation. Clicking on that will take us to the GUI interface, where you can specify the simulation parameters. So as for simulation parameters, we have accuracy. So for accuracy, if we move the slider up, it will actually make the mesh more finer. It will actually reduce the cell size, and it will make the mesh more finer. And then we have maximum coordinate number. Coordinate number, or the CFL number, as we all know, is the dimensionless parameter, which determines the stability of the numerical simulations. If the CFL number is greater than 1, it will lead to inaccurate and unstable simulation. And in AIM PravaH, 0.5 is the default value for the maximum coordinate number. And then we have as simulation parameters is performance. Performance determines the computational speed and efficiency. Increasing the performance slider will actually increase your computational speed, but it will actually increase the mesh size also. Like it will reduce the computational time, but the mesh size will be larger. And then we have data saving frequency. As for data saving frequency, this is the parameter which gives you the frequency at which the result files will be saved during the simulation. And then we under the parallelization sector, we have the option for physical CPU processors. That is, you can specify the number of cores. So why do we have to specify the number of cores? Because specifying the number of cores will actually divide the computational domain into that number of cores, and each subdomain will be fed into each core for parallel computation. And the next, as boundary condition, we have thermal gradient at substrate boundary, which is there to realistically simulate heat diffusion at the boundary. And then we move on to WLAM execution. This is the part which actually ties everything together, WLAM execution. So here you can see in the execution part, there under the execution part we have save all option. Clicking on the save all option will actually save all the default parameters or the new parameters that you have added, material properties, process parameters, simulation parameters, everything. And clicking on the run solver icon just below that will actually start the simulation. So there is another one icon which is launch console. So launch console actually helps us to obtain the recent status of the simulation, like the storage used, the percentage of the simulation completed. As you can see, on clicking on the launch console, this is one simulation that was running, which you can see is completed. It shows 17%. So launch console actually shows you the recent status of the simulation. And then after all this, as the simulation is completed, when it is 100%, we can go to the show results to obtain the results in the PravaView. So now I'll show you one of our case studies where these are all the material used, that is Ti-64 alloy, shielding gas, argon, leisure power. We have given 1200 watt, leisure speed as 0.016 meter per second, leisure spot diameter 2.3 millimeter, track length 16 millimeter, wire radius, wire feed angle, preheat temperature, scan pattern is single lead position here. Accuracy we have considered 50 only, and the number of cores we have used is 8. So I will show you in the hands-on section like how to visualize all this in PravaView. So this is the PravaView visualization. As you can see, this is for the initial time step. This is for the initial time step where the simulation is just started and the melt pool is not yet created. You can obviously see. And then, yeah. So next we go to the PravaView visualization, that is a slice operation. So what is the slice operation? By slicing operation, we can actually obtain a view of the cross section of the solid, melt pool, or the wire as per the user's needs. This picture actually shows the slice of the solidified beam. You can see this is the cross section of the solidified melt pool with the proper temperature range for the case study that we have used, and then we will show the slice of the melt pool in the liquid state at time step 0.32 seconds. So by using the data axis grid on the slice of the liquid state melt pool, we can determine the melt pool height and the width. At time t equal to 0.32 seconds, we have got the melt pool height as 1.8 millimeter and melt pool width as 2.4 millimeter. Moving on, we are going to the PravaView visualization glyph operation. So what is glyph operation is that by using this glyph operation, you can actually show the physical quantities that are related to the melt pool, like the velocity, pressure, temperature, in the vector forms. Like we have here, we can specify what physical quantity the vector arrows will represent, like velocity or pressure, and how the color range will specify the different magnitude of the same at different points of the melt pool. So this is the glyph of the liquid melt pool at time equal to 0.32 seconds. This is the pictorial representation with different color arrows. You can see here the maximum temperature recorded is 3099.1 Kelvin, and maximum velocity as recorded is 0.42 meter per second. So as you can see, these are the different colored arrows which are actually representing the velocity vectors, and also you can see the temperature range of the melt pool here. And then we come to the comparison of the melt pool with the experimental results. So as you can see, the slice of the solidified melt pool at t equal to 0.52 seconds. This is the This is the slice of the solidified melt pool. Now you can see this is the observed result from PravaView, and below it we have the experimental results. So the melt pool depth and the width determined from the data access grid in PravaView actually matches with the experimental results. And then we are going to show you the animation of the simulation. That is, this is a video representing the WLAM simulation based on single layer deposition with Ti64 alloy as material used, and the experimental results are there, so you can find a similarity between the bead formation that is happening. Yeah, so here I'll ending my presentation. Now we will go to the hands-on section. Yeah, so I'm going to run one WLAM case in AIM PravaH software. Let me share the screen. So now I'm going to create a new project. As you can see, this is the place where you can add the project name. You can obviously load project if you want to load old files, and you can create new by giving a new name. So suppose this is. So after writing the project name, you have to click on create new, and in create new, you have to select the folder you wanna save the file, and then OK, and then you have to go to macro skill WLAM. So as I've already showed you in the presentation, first thing you have to do to go to the material section. Here you can see this is clicking on the material section will move you to this interface where you can choose the alloy of your desired. This alloys are already loaded as default. So if I select Ti64, you can see these are the solid alloy properties which are shown here, which are already loaded in the software. Changing onto a different alloy will change all the solid alloy properties. And you can also create a new alloy by selecting on this icon. So for now, I'm selecting the most usely alloy, that is the Ti64 alloy. And obviously, default values are already saved in the solid, molten alloy properties, the vapor alloy properties. And then we can select the shielding gas. So I've already represented. There are three default shielding gas values: uh, argon, nitrogen, air, and you can obviously create a new gas. So for now, we are selecting argon, and this is the place where you can specify your shielding gas properties: molecular weight, specific heat, dynamic viscosity, Prandtl number, density, etc. And then after all of this, you have to click on save. So after clicking on save, you have to go back, and then you are going to click on the process parameters. In process parameters, the laser beam component, as I've already said, if you want your laser to be directed downwards, it is obviously -1 along the Z direction, and then you can specify power. As for the validated case study, we took power as 1200 watt and the spot dia as 2.3 millimeter. So this is how you specify your properties. And feed angle was 25 degree only, and as feed rate we took it 0.0133 meter per second. So this is the feed rate, and now we have to upload the scanning pattern. Upload scanning, as I've already said you, there is by clicking on uploading scanning pattern, it actually moves you to the WLAM project directory, where you can see in the data section this default scan patterns are already there. So you can obviously click on any of them, or you can create a scan pattern of yourself and then save it in the WLAM directory, and that will also show up here. So now we have the default patterns. We are choosing pattern default.csv file. So after selecting all this, we have to click on save again, and then you have to go back. And for the simulation, you can obviously move the slider up and down um, just the way you want your simulation to happen. These are the maximum coded number, performance, data saving frequency. I'm keeping all these at default and then saving it. You can obviously change it if you want. And then after saving it, you have to go back. And for execution, you have to save it all, which will save all your parameters. You can see this is the file uploaded, preparing solver ready to run. After clicking on save all, the solver will be ready to run, and then you have to go on to click run solver, which will actually start your simulation. And as you can see, this is the launch console icon. Clicking on the launch, this simulation hasn't yet started. So when it will be like some 10% or 20%, and see, this is the printing have already started. Start time 0, end time 0.375. So after some time, when the some percentage of the simulation will be completed, it will show that how much percentage is completed or how much is the elapsed time and all that. Yeah, here you can see, clicking on launch console will show you simulation completed. So now from here, the simulation completed percentage is really very less, so I don't think any results will be shown. It will take some time. So if you click on the show results, it will actually move you to the PravaH visualization. So in PravaH visualization, you have to click on WLAM form. Yeah. So if you have to do this skip 0 time and then apply to actually start the simulation from the initial time step. So going to the initial time step, you can see the melt pool has not yet been created because simulation hasn't been completed much. So clicking on the pause button, pause and play button, you can run your simulation. So as of now, I can load another result of mine where I can show how to create the operations on the melt pool. So I'll just close it now. Simulation launch console. Yeah, simulation is going. So from here, you have to go to load state, and then another file I'm just opening. So you can see in this result file that melt pool has already been created. So again, you have to do skip 0 time to start the simulation from t equal to 0 seconds. Yeah. So now what you have to do. Yeah. Now, as I showed you that we can do the slice operation here. We have to play the simulation, and as you can see, the melt pool has been created. And if you notice the boundary, you can also see that solidification has also started. So if we want to do this slice operation on this solidified part, we can select on solid, and then we can go to this slice operation is there. So this slider you have to move according to your own choice where you want to run the slicing operation. So here you can see I can move the slider horizontally wherever I want. This is the place where I want to do the slice operation. So I'll move it here and then I'll apply. So the other wire and the liquid parts, I will hide all those so that I can focus on this cross section. And here you can see it in different orientations. So yeah. Now here we can specify the parameter which we want to show. It is selected pressure. If we want to see the temperature range, you can see selecting on the temperature range. It is Yeah, selecting on the temperature range, it shows the color range, and you can determine from here the temperature at each at different points of the melt pool. Now, if you want to find out the melt pool height and width, you can click on the axis grid. So clicking on the axis grid will actually help you determine the melt pool width and height, and from here you can determine how much width or height of the melt pool that has been created. And now we go to the glyph operation. So I'll hide this slice thing, and I'll again show all those solid and wire and liquid. Yeah. So this is the last time step that I'm working on. So selecting on the liquid, I have to click on glyph operation. In glyph operation, yeah, in this glyph operation, you have to select the input array. That is you have to select the physical quantity that you want to show as velocity vectors. So here we're selecting velocity, and then we're applying. You can see the velocity vectors are being created here. Velocity vectors are being created here, and yeah. So by in the coloring range, you also have to select the velocity vector, so that the color they are colored differently to show the different magnitudes of the velocity at different points of the melt pool. So zooming in, you can understand the different arrows are colored differently to show the different magnitudes of velocity at different points of the melt pool. And yeah, this is how you can operate the glyph on liquid part of the melt pool. And here you can take screenshots, obviously capture screenshot at different time steps. Suppose you want to take a screenshot at 0.92 seconds. So you can click on this icon. This will actually open a file in your project directory only. You can specify the file name and then OK. Here there will be screenshot options come, which will help you to specify image resolution. So these are the default values, and you can click on OK. And then you can also save the animation by in the file on the file you have save animation option. You can give any name and then save it. Here you can specify the frame rate if you like, if you want to compress the file or reduce the frame rate, you can do it here. And then you have to click on OK, and your animation will be saved in your own project directory. Yeah, this is it. So yeah, if you show it is showing bad simulation, you have to close it. You have to try again, or you can contact the support engineers in Paanduv applications.